Sorry, just give me few minutes, huh? Okay. It
Okay, sir, no problem. Okay,
file
sir.
is trying to load. Just give me some
No
time.
issues.
Is my slides getting visible?
Yes, sir, it is visible. You are audible as well. And the slide is not in presentation mode. Now it's in presentation.
Now is it in
Yes,
presentation?
yes, it is in presentation mode.
Okay,
Perfect.
thank you. Sorry, the file was little larger. It was trying to take some time to load.
Okay.
Okay,
Okay, sir.
so thank you to Dr. Kiran for having me invited to this ATAL program on faculty development program, and I think you are discussing about a lot of advances in the manufacturing in general, and specifically at this talk, we would try to look at additive manufacturing and some of its application. And since mostly I have worked on the design for additive manufacturing, that means how we can enhance the applicability of 3D printing or additive manufacturing by design innovation, or what are the design considerations, or what are the design tools that we have to look at when we want to utilize additive manufacturing in a disruptive fashion or in new applications. And since much of my work is in the biomedical area, I will be taking a lot of applications. Specifically, I may not talk about all applications, but I thought for today's discussion, I will talk about some of the interesting works that we have done in the area of biomedical application. So I am part of this Center for Excellence in Additive Manufacturing, which has been set up in IIT Madras, and we have in in our institute we have uh, many different additive manufacturing facilities, including metal 3D printing. The first machine we installed in the year, I think 2021-22, during COVID time. We had the first 3D printer. In fact, that was the first 3D printer indigenously developed, made in India, from a company called Intech, and uh, we collaborate extensively with them to improve their process as well as the design methodology. And more recently, we have acquired a larger machine, also a build platform. So we do a lot of different applications. As I told, for today's talk, I think my let me see if you are able to see a laser pointer, right? I think it is better.
Yes, sir, it is visible.
Fine. Okay. So today, even though I will be talking mostly about the biomedical applications, but we have done a lot of different applications. And here you see on the left of your screen, we have printed a H13, a very difficult to print alloy, which is very high hardness, like HRC close to 60. And while printing itself, there will be build failure. That means because of the high residual stresses, it will crack, and the part will separate from the build platform. So we did a lot of work in trying to optimize the process parameters. And here what you see is a forging punch application. The original punch is having this design. It's a warm forging die tool, and it's a four-stage process. As you can see here in this forging setup, it's a four-stage punching process, and the final punch is what you see here, the fourth stage punch. And it was a solid punch, and it was wearing too quickly the conventionally machined tool. And for every I would say batch, or a 8 hour shift itself, they had to stop the machine, change the tool, because for every 2000 parts or so, it was wearing, or it was showing cracks, because of the temperature, high temperature, and the stresses. So we worked with the industry. We developed this warm forging tooling punch with these internal conformal cooling channels, as you can see here, after several iterations. So right from optimizing the process parameters, because it's a difficult to print alloy H13. And then we also worked with the design aspect. We modified the design to include the conformal cooling channels. And now I'm happy to say that this tool, the a batch, or parts that it is able to punch, is close to about 20,000, from about 2,000 to 2,500 parts. On an average, it is going above 18,000, uh, uh, and many tools have also survived for 20,000 parts. So it's a kind of innovation. Now this industry is using many more conformal cooling channel designed tools for such warm forging application. So this is one interesting application that we have very recently done, and we have patented the design, and it's an industry translated work that our group has done. As I said, it's not a single man's forte. I am a design person. I exclusively work on design for additive manufacturing, and some aspects about modeling and simulation. And there are material scientists, high temperature, metallurgy persons, post processing, surface engineering, and many people were involved in such a work. And here you see another interesting work where we designed a very complex shape. As you know, additive manufacturing, it is possible to build very complex shapes. So this is a gyroid inspired design, but it's completely novel for heat exchanger application. So where as you could see here, this is again a patented design. So here as you can see, these are the pathways for say the hot fluid, and you have the cross flow configuration where over this tube you have the cold fluid, and uh, the design has been optimized, the topology as well as the shape, such that it is able to give um, enhanced heat transfer with reduced pressure drop characteristics. And many of these biomedical applications, anyway, as part of the today's talk, I will be talking. So the whole concept is that we can now fabricate using additive manufacturing a design which considers performance as the main objective or attribute. Because always in engineering we have conflicting objectives, there are manufacturing difficulties and many other constraints. But additive manufacturing takes you more closer to what we can say as a performance first, or giving importance to the design. Whatever is required from a functional perspective, that can be achieved in a material that is of choice and as per the say service conditions. So it is taking closer to that, even though I wouldn't say that we are completely there, because as with any manufacturing process, additive manufacturing also has its own say issues that, like I'm not going to introduce the process itself. I believe many of you may be aware of additive manufacturing. So it needs support structures. There is a support removal process. There is a surface finish issues are there. There is an anisotropy that is coming due to the layering effect, because we are manufacturing using a layer by layer process. There is an anisotropy that is involved, and also in metal additive manufacturing, as I told, there are residual stresses and distortions. So all these issues also are there. As any manufacturing process, we have to also overcome many of these challenges and innovate using this process. So, as I said, today my focus will be to give you a broad perspective of DFAM and take you to one domain of application, that is medical, and look at how AM is advancing many of these fields, particularly they are in the medical community, how we can advance some of the clinical applications of additive manufacturing. So, as a methodology, even though I may not be presenting many of the aspects of DFAM, but I want you to have an appreciation that when we want to develop an application, uh, we need to look at the design. So unless we re-look at the way a design has been made for that particular application, we may not be able to completely exploit the capabilities of AM. That means what has been, let's say, a component is there, if we try to just make it through AM, we may not be economically viable, neither we will be achieving any additional benefits. So we have to look through the design, uh, considering an application, and do a redesign for additive manufacturing. So when we look at that, we have two aspects. That is one, which is the restrictive aspects of any manufacturing process. Like as I said, any conventional manufacturing process, we do DFM, design for manufacturing, to look at the design from the perspective of manufacturing feasibility. The same is true in case of additive manufacturing, where we might have to look at what kind of surface finishes are possible. Let's say if we have these internal features, I showed you an earlier example where there is a conformal cooling channel and we are making this uh, through additive manufacturing. If there are going to be support structures which will be required for those internal features, we may not be able to remove them. Or if we are building, say, something like lattice structures, and if the lattice sizes are too small, the powder which is getting entrapped, we may not be able to take it out. So many of these things needs to be considered. That's what I mean by restrictive, or what may be constraints when we do a design. So support structure is one thing, removal of support structure, and internal features are there. So then finishing may be an issue, even though we may have, say, some abrasive jet or other such processes which can be used to do some kind of a finishing for internal channels. Again, that is a issue or a challenge that one has to consider at the time of design. External surfaces, surface finish can be improved. You may give some machining tolerance and do a finish machining. Again, because we use AM for making complex geometry, it is possible that there may be undercuts and it's not possible for you to machine all the surfaces. So there are a lot of studies or people work on how to optimize the process parameters for the down skin, or what we call as the surfaces which are in contact with the powder while it is being built, so that the surface finish can be improved. Or supportless manufacturing, how we can optimize the process parameters in the laser powder bed fusion, because mostly we are now into metal fabrication for real world application. So my talk is not just restricted to, say, some polymer processes, because this process originally, when it was evolved, evolved as a rapid prototyping technology, where people predominantly used polymeric processes for making prototypes. But today we are talking about manufacturing. We are talking about manufacturing end use components in the material, whether it is a high temperature application, turbine blades, conformal cooling channels, and printing of turbine blades, those kind of applications where fuel nozzles and so forth. So we have to consider these, and we need mathematical models, simulation models that will describe how these process parameters or attributes influence the design. So a lot of modeling happens here to tell how, let us say, choice of process parameters will affect your surface finish, or maybe the cost, maybe the anisotropy, the strength of the component, the cooling rates. Let's say if we have the LPBF additive manufacturing, the cooling rates and how the thermal history is there thereby you can predict, let us say, the distortions and residual stresses. So lot of modeling, that's why this modeling and simulation becomes very important. And then coming to the attributes, basically am we go for making complex geometries, and since we are adding material, we can also do what is called as a compositional control. In the sense, we can change the material composition or functionally graded parts. In conventional manufacturing, typically we achieve functional gradation using, say, some surface treatment, heat treatment, night riding and processes like that. But here, by changing the, say, in a given alloy system, it is possible to change the alloy, whatever is metallurgically possible, so that you can deposit materials with changed um, uh, composition, and thereby it is serving, say, different purpose. So it is possible to have some place where the hardness is high, and maybe in another place the toughness is more. It is possible to do those kind of alloying, and so the design capabilities of take care of it. In the sense, uh, traditionally we had CAD systems which were only based on, say, surface models. They were not volumetric models. In the sense, the CAD files didn't have a description
Pulihoran.
about how the material is distributed inside the model space. Uh, Dr. Mani, can you mute yourself? Your voice is visible. We are hearing you, I think. Yeah.
Yeah, I'll
Thank
mute
you.
him.
Thank you. Thank you. So when we have these kind of models and simulations, it is possible to predict the performance of the AM component, and we can develop better applications. And all of this we do to uh, achieve some of these application domain, like we try to either um, make a customized part. So today a lot of customization can be done. We need not go for large scale manufacturing. We can have small batch production, and customization is possible, because with AM it is possible to build, say, in the medical application which I will be showing, we talk about patient specific implants. So specific to patients we can develop the implant. So challenges here are, like, how do we quickly design or develop this customized design? And we can also do a lot of this replication today, because of many say, changed manufacturing logistics, and the supply chain disrupted by changes, let's say war and other thing. Many times, we have legacy components for which we may not be able to source the say components, or we have a system and we are not able to maintain because we don't get the spare parts. So there are many strategic application, including military and other equipments, where it is necessary to um, have these, so that we don't compromise the the application. So replicating or manufacturing, so what we traditionally we call reverse engineering some components, trying to make not getting the parts from, let's say, OEM, but rather trying to make it so that the system life and maintenance is improved, and we can do localized manufacturing. So today we talk about manufacturing in space. So how AM can be an enabling technology, so that manufacturing can happen in, say spacecrafts. So how do we locally develop the capabilities to manufacture? So rather than expecting long, supply chains, or which involves sourcing material, manufacturing at different places, and transporting. So many of these things can be relooked at in the context of additive manufacturing or use of it. So like that, every keyword that I have put through in this circle uh, is an area in itself to explore how AM can be used to change. So we talk about consolidation of parts. So assemblies, we can reduce the assembly step. Precision assembly, costly assemblies can be avoided. We can combine the geometries parts. The geometry may become more complex, but with additive manufacturing, it is a key, because the key advantage of AM is it can make very complex geometries. And unless we develop designs which try to um, exploit this capability of the process, we may not be able to succeed in developing good application. So always when we develop application, we always look at reducing cost, reducing time to manufacture, but at the same time improving the quality. So this is a kind of like a pyramid where, or a multi criteria, multi objective optimization, where I'm trying to reduce time, cost, but also at the same time trying to increase the quality. So this is a big picture that I just thought I should present to you, because underlying, even though I may not explicitly state these things, underlying every applications that we have done, many of these things have gone behind the thought process in order to develop a successful application. So as I said, yeah, I do not know whether how everyone is placed with respect to the understanding of AI. I'm just one slide of trying to understand how this process and property relationships are there. So as you would see, the AM has a lot of process parameters, including build orientation, let's say layer thickness, how you hatch or how you infill the material. So all of this influences the outcomes. So the outcomes could be in terms of the part quality, it could be the cost of making of the part, or time to manufacture, how much material is consumed. Because in different orientation, some will require less support, some may require more support. Typically the support structure is also made in the same material. Let's say if I am working with a titanium, medical grade titanium alloy, to develop a implant, the sacrificial support structure which will be generated is also made of the same alloy. So that means that material, the support is going to either it has to be recycled or it has to be taken out. So all that becomes a consideration. um, so these are some of the parameters, and you have in specific to each process. As you know, additive manufacturing, there are about 7 processes classification wise. So like fused filament fabrication, to vat polymerization, to laser powder bed fusion. So each of these process parameter has its own manufacturing associated processes. Like if you consider LPBF, it will have the laser power density and the characteristics of the laser. All of that will also dictate how we optimize the build parameters. And when we try to optimize, we always consider how the performance of the component which is fabricated is influenced by the process parameters. So many characteristics can be looked at. So I broadly say it is cost and quality. So quality, again, from a perspective of additive manufacturing, we can talk about the finish quality, like form tolerance or surface finish, and mechanical characteristics like part strength. So each of this is influenced by many parameters, including what is the process that you have chosen, what is the material to say build parameters like what is the orientation. Let's say if this is a component, how you are orienting it. All of that dictates uh, each of these characteristics. And uh, a lot of literature is available where people have tried to model or understand the effect of these process parameters on these characteristics. And including in our group, we have done a lot of work on developing some of these models, and also look at a multi-criteria optimization. Now that if I have, let us say, models that can predict, say, surface finish of a component, say it can predict the mechanical response, let's say the strength of the component, and let us say the cost, like as I am showing in this example, a simple, let us say, a connecting rod example. So if a connecting rod is aggregated in different orientation, what could be the cost, what could be the strength, and what kind of form tolerance or geometric tolerances and surface finishes that I will get. So once I have such a multi-criteria uh, space and the models that are available to me, I can do a optimization, a predictive analysis, and choose some of the best parameters to build the component. So just to give you some idea, some cost models exist, like the how the build time is influenced by say choice of parameters, like you have the time to build, say the material that is required, and the energy that is going into building it. uh, so time and cost are both important in additive manufacturing, and a lot of uh, work has happened to understand this or predict these attributes. So like here you see a medical implant here, it's a cranium implant. So if I choose, let's say, some specific orientation, you can see that there are a lot of these kind of support structures. So if I change this orientation, maybe the support requirement is different, the time to build is different. Typically in am, the height to which we have to build the component dictates the time and also the cost, because it's a layer by layer fabrication. So a, a low fidelity model can just be a model which is based on, say, model height. But as you would see, model height is not just good enough to tell about everything, because let's say if I have a sphere and I have for the same height this kind of a human face model, or say some other geometry, the support structure requirements and other things are different. So there are works that include this support volume calculation into estimating this cost and time. And even there are models, or people have developed models where the hatch, how the material is being filled, like what is the contour, what is the contouring time, what is the say the hatching time. Hatching means infilling, the interior has to be filled. The contouring is the periphery, because when you slice the CAD file, each slice is made, you put one contour, the periphery, and then you also hatch or you do the infilling. So models have been developed to consider including all of this, to estimate, give you as good as an estimate to the cost and time. But as you will see, each of these model has its own computational complexity. So if you would like to explore this from an optimization perspective, you have to look at different combinations of this, and it is always better to have a model which is computationally less expensive. So in fact, in our group, we have just worked on an hybrid framework where we start with, say, some low fidelity model. That means initially we just look at height of the model or some parameters which is not very expensive to compute. And as we proceed, because typically optimization is an iterative process, as we proceed, we go to an more higher fidelity model, or I would say a complex model where we also compute, let us say, the support volume or the material addition and so forth. So many of these papers or works are available in my webpage. If more, you are interested, please welcome to look into that. So there is a lot of complex geometry that can be done. This is something that I had shown just before. So this is the complete embodiment, as you can see here. This is a gyroid inspired design. So as I told, the conventional CAD systems are based on explicit modeling. We use the concept of half space and boundary representation, where the boundary, which is typically for a volume, it is a surface, which is what is represented. A surface is a half space. One side is the material and other side is the non-material. So we don't uh, explicitly represent the interior or the volume as a function, but the mathematical description is only for the boundary. And that's why these modeling frameworks, all CAD softwares are based on this brep, or what is called as a boundary representation. But with this advent of additive manufacturing, because we are able to um, build complex geometries, it is possible that we can um use now what is called as implicit geometry. So here uh, it becomes like a function. I can say like f of x comma y comma z is a function. So that is an implicit model. And if I equate that and I want a specific contour of it, like it is equal to 0, equal to 1, equal to 2, that gives me the surface. So the model is inherently a volumetric model, but for the purpose of, let us say, printing or for any post processing, I can always convert that into a surface model. So so this implicit to explicit uh, can be done. And nowadays there is more interest to look at this implicit modeling. So one of these is the your mathematical implicit functions, like this triply periodic surfaces, gyroid surfaces. And here what you see is one such configuration. But what I would like to impress upon you is that the CAD systems have to move from an explicit, uh, surface based modeling method to more of an implicit geometry, where the geometry is nothing but a mathematical function which is describing the volume and not just the boundary. And that is what I am interested to convey. So in the context of biomedical applications, just before we look into a lot of these applications, in general we will be working with internal anatomy. So thereby we will be looking at some medical imaging modality, non-invasive way of acquiring the interior geometry details. We typically work with CT, MRI, and other such, mostly used is CT and MRI, even though other technologies like ultrasound and some of these can also be used in specific applications. So these imaging modalities gives you the internal geometry. And using medical image analysis and processing, the region of interest could be assessed or segmented, and one can develop the models. So either the anatomical models for certain applications, or use these anatomical features to model some implants or other such construct. Even orthotics and many other devices can be made. But the essence is that we are looking at the human anatomy and deriving the features for our design by processing this data. So, quickly, I think a typical medical imaging protocol like CT would look something like this, where you would be able to see a axial view. You will be able to see the anterior and posterior in the sagittal view, and this is the the coronal view, where you can see the it's like a front view, so where you can see the right and left, or the medial and the lateral side of the body. And the region of interest, in this case you are seeing a CT image, so uh, the region of interest could be some bony features, and one could segment and extract out, let's say in this case, a femoral geometry, as described here. um, so I would not spend much time. In the interest of time, I would, but in general, the whole process goes through processing medical images, removing the noise, doing some contour reconstruction, developing the surface model. Uh, so we use many digital signal processing or image processing methods, like noise filtering, to thresholding. Basically, thresholding is to uh, demarcate the region of interest. Typically an image is uh, what we call as a Gaussian mixture model, because there are many tissues or many different types of contrast will be there. So there will be like one Gaussian will be there. There will be another Gaussian. So you can see it will be like a mixture of several Gaussians, and the thresholding is basically trying to uh, find. Find an intensity which can demarcate, let us say, two Gaussian, because it is a spread. So you have to just choose something which will adequately separate the means of the two classes, or the clusters. So that way you could identify a particular tissue or a particular um, anatomical feature. And once you have done this thresholding, you can convert that into edge boundary, which is basically the contour. So you can find the, by taking a derivative of that image, you can do this edge detection and obtain the edges and develop the contour. This is a whole process, and finally develop the tiling surface, or what is called as, um, because contour by contour it is reconstructed, and you put together the faces. So because I'm going to talk many medical application, I thought you should just know how it is typically done. In our group, we have done a lot of work in medical imaging and image processing application also. Some of you are interested, you can go and look into some of the papers on MRI processing, CT image processing, and so forth. Okay, so these are some works on um, developing some efficient algorithms for segmenting. And I actually extensively collaborate with specifically in the orthopedic domain, spine surgeons. So a lot of work we have done in the area of spine, so some works you will be seeing. So coming to applications, so a lot of applications have been done in the medical domain uh, using additive manufacturing. One of the applications which have been extensively exploited is how do we do surgical planning, and so before going to the operation, how well the surgeon can go prepared. So typically the non-invasive images like CT, MRI do show the internal anatomical features, and doctors can plan for the surgery based on that. But giving them a tangible object, like a physical, say, a model of the three-dimensional anatomy, gives them scope for, let us say, rehearsing the operation, and some complex vascular surgeries, some complex, surgeries where the risk of, let's say, um, deviation right from the planned operation could be a very costly affair. So in those perspective, we see there is a good application. So one application I will just showcase, even though we have done many applications, this is a scoliotic spine correction surgery. And I work with one, as you know, this is again, a problem which is mostly because of, there could be many reasons, congenital, people also say malnutrition, many things could be there. But mostly, the developing world and low economy countries like India, we have a lot of patients with this scoliotic condition. As you can see, this is an unnatural curvature of the spine. So not only does that gives uh, a visual growth problem to the child, but also, as you can see here, there is a lot of constriction. It's not only the way the person is able to carry himself, but it's also how his lungs are able to breathe, and he cannot fully utilize the capabilities of the lungs, and in very severe cases he may have a lot of breathing difficulties and so forth. So the amount of correction that is possible depends upon many factors. And because this vertebral column is also containing the spinal cord, and it is very important that the dura of the spinal cord is not too much stressed in this process of correction. So it's not like a tube, like in a mechanical sense, I can just pull it or make it straight. But it is having those nerve bundles, and it is very important that the operation is planned. And typically what the doctors will do is they will put some screws and rods, and when placing these screws, again he needs to have a correct idea about what kind of screws, what sizes of screws can be put. Typically these operations are done on a adolescent patient, because that is the time mostly they come for this operation intervention. If they are able to afford it, early detection and early correction is always better. But many of these patients actually come when they are almost towards their end of their growth period, like 15 years, 16 years, all those that is what the government hospital setups typically see in India. So here you see that there is a 3D printed model of this spine. So the doctor is, for each patient, the articulation is different. So typically, a spine surgeon with good experience will know the articulation of the spine, the curvature of the spine, how a cervical spine will be curved, or how the say lumbar spine will be there at a particular age and all. But these are deformed spines, and each spine is different. So it requires more experience. So this technology can also help to, let us say, a doctor who is not that very experienced, like more than 20 years, but rather, let's say, a doctor with 5 years or even 10 years experience is also able to achieve the outcome quality similar to that of a very experienced doctor. So what you see here is a 3D printed spine, and these are those K wires, basically to understand the orientation of the pedicle screws. These are the pedicles. The pedicles only, they put the screws, so they know in what orientation they are aligned, and thereby and what kind of correction is possible at each segment, how much of the bone can be resected. All of that is pre-planned, and uh, the doctors do the surgery. So here I'm just showing one case. I extensively work with this doctor in Madras Medical College, and we have done many cases, more than 20 cases where we have intervened just to understand. what is the control case is like if I am not using, let us say, this 3D model aid to do the pre-planning, what kind of outcomes are how my outcomes are improved with the usage of this technology. So this is what I was telling, they put these rods and these screws. The screws have to be correctly chosen, otherwise the screw breach is an important issue, because these places are lot of vasculature is there, lot of big blood vessels are there. If there is a breach, it can go and damage the spinal cord, and so the outcome qualities are better and improved because of this better understanding of the anatomy. So coming to another domain where one of the other important application is we can develop what is called as a patient-specific implants, or we can customize the implant design specific to the patient, so that the functionality is improved. Many a times the operation times are minimized, and the form and fit is good, the post-operative recovery is better, and so forth. So we have developed many methods specific to some 2 3 types of implants. This is one of our first works where we looked at this patient specific implants for the total hip replacement, the femoral prosthesis. So here, as you understand, this is a hip joint, and uh, so here this is resected. This portion, as you can see here in this model, this is resected, and instead you have this femoral stem, and you have this ball which is articulating in the acetabular cup of the hip. The operation itself may be required because of, say, arthritis, old age, or tumor, or maybe sometimes because of trauma, accidents, and so forth. So, in some case, in the cases where the um, the bone shapes are quite different. So many of these implants, the standard implants, even some of them come with what is called as a modular implant. But several studies have shown that the Asian, the hip and the bone anatomy is different from the Caucasian anatomy, and always a customization gives some better outcomes. Here, as you can see, the design methodology I was telling, because in a mass produced component, the design cost is uh, taken over on fabricating many components. The cost of the design is becomes a overhead on a large number of components which are manufactured. But in a patient specific implant or customized implants, the design cost is to be taken up by that particular implant only. So thereby, the cost of making such implants becomes exorbitant, and many times the patients may not be able to afford such a cost. So the design cost, how can we look into that? So here we have in fact developed several methodologies for automating these design steps. So we have developed geometry modeling tools to process these geometries to extract uh, excuse me,
Yeah, I'll take
RK,
care.
yeah, Shakya. Okay. So, uh, so the geometric processing to extract these features and to develop this design to check for the form and fit of this implant, uh, and also to understand the mechanical performance. So how, let us say, this implant will perform, because the mechanical forces, particularly this being a long bone, large amount of forces it is carrying, the force redistribution, how the force gets transmitted to the bone. So what you see here is uh, a simulation model showing how the implant and the bone, the resected bone, construct together. They will perform. There's something called as a stress shielding effect, and what is its influence on, let us say, the bone atrophy and implant loosening. So all these things we considered to develop patient specific implants. So the lot of these steps have been automated by developing design methodology. And we so this is just yeah, showing the same thing in a larger picture. Yeah, the final element, jigs, and where, step by step each of these are done to come up with the design. So this is the one of such design, which we more recently developed it for a cancer patient of age about 16, 17. That patient's geometry for that size, no implants was available, and thereby the doctors needed a patient specific implant. And because of the tumor, large amount of resection of the hip and the bone was necessary. And they wanted many other features also apart from the standard the implant that we had. And we had developed, even the length of the implant could be changed, because on the operation table, if the oncologist says that some more amount of bone needs to be removed, or the bone needs to be, the tibia bone has or the femoral bone has to be removed, in this case, they needed a longer implant also, it could be accommodated. One of the other areas where we extensively work, specifically with the voluntary health services hospital located in Chennai, is on developing patient specific cranioplasty implant. So as you can see, this either because of trauma, or sometimes the the cranium, the bone of the skull, right, that let's say if it is um disintegrated, and to allow for the brain to heal, because it will swell, they typically cut and remove. And once let's say the healing has completed, both for cosmetic reasons, as well as to prevent this external atmospheric pressure from unduly pressing the dura. That means the dura is the layer above the brain, because otherwise what happens is, in some of the cities we have seen in X-ray images, how the brain actually, like a crater, it will go inside because the atmospheric pressure, it is pushing it. And there is something called midline shift and all of that, which the doctor, so from a functional perspective also, this reconstruction is necessary. So this picture just shows how traditionally people they do is using the POP. They develop the a model from the patient. You can see here, this is a patient's head. Actually, on the patient head itself, they, like a mold maker, he makes the negative of that, and using that negative, we again make a positive. So this is a PMMA implant cast, and then you can put some holes so as to put the mini plates to anchor it. So this is how the traditional way of design. So what we have developed this, again in this case, we looked at this design workflow to do an customization. So as I said, in each application, the design workflow becomes important. Then only we can. This is what I was telling in the upfront. DFAM is very important. How we look at an application from the perspective of AM, and how we develop, say, design workflow. So again, in this case, we looked at developing the cranium plate. So this is, like I said, this is the opening. In some of the X-rays, you could see that it forms like a crater. As I am showing using my laser pointer, the brain itself will be pushed like this because of the difference in the atmospheric pressure. even though you don't see that clearly here, but in some x-rays you can see that there is like a crater, the dura will be pushed. So this is a unilateral defect, that means on one side. So it's possible that the geometrical features of the other side could be chosen to create the patch which will close this hole, and then one can develop the implant. So this design workflow we have automated, like some steps, like if I have the 3D reconstructed model from the CT, how to automatically identify the midplane. So because this midplane identification is important to know what side is the healthy side, or we have the geometry which can be used to reconstruct the defective side, or where the hole is there. And then you can use some computational geometry procedures like hole identification to identify the boundaries of the hole, that is hole detection. And then maybe using surface b-spline surface modeling, you can take the surrounding uh, the points or the data to have an approximation to this hole, so which is what you see here. And uh, develop a trim surface, just cut it based on this hole that has been identified, and develop a thin component. And post that, you can add say some filleting or other say some small flanges to put the screws and so forth. So this is a workflow, and many of these steps we have tried to develop an automation from the reconstructed geometry. So I have worked with couple of doctors to implement this. So one is this doctor who is earlier he was in CMC Vellore, now he's in Jaslok hospitals in Bombay. And here what he actually does is he still prefers a PMMA implant. So after developing this implant design, what he does is he goes for the negative of that. That means a mold of that is made, and using the mold, like here, in the hole, he pours the PMMA, gets the PMMA part, and he does the implant. Because some doctors still prefer to use PMMA as opposed to, let us say, a metallic implant, titanium implant. So in this case, he uses still this 3D reconstruction, this method of developing the um, model, but a negative is made, and he makes the positive using a PMMA. But what we do here with this VHS, which is a hospital with whom I collaborate, so here more than 20 patients we have given titanium implant. So as you can see in this picture, this is the implant, and it is lightweighted using some kind of a mesh geometry. And the shape of this implant, as I told before, it comes from this CAD reconstruction. So as you can see here, this is the way, this is like the crater you can explicitly see here in this patient. The brain is pushed inside. And this is that implant uh, while it is placed. Some pictures shared by my doctor colleague, and this is post surgery. As you can see here, um, it's nicely reconstructed if you could compare it with that previous image. So this is, I think, after I think 2 weeks of surgery, 1 or 1.5 weeks of surgery. So we can also look at the post-surgical CT and look at the form and fit characteristics. So we analyze how the form and fit and the reconstruction, how good it has been. From in a more, I would say, rather than qualitative, you can do a lot of quantitative analysis as well. One of the other patient-specific implant work that we have been extensively doing is maxillofacial implants, and with this COVID, actually post-COVID, there was a problem called black fungus infection. I think some of you might be knowing that because of these the steroids and other things that were used, the immunity is compromised, and the black fungus, it's a kind of fungus, it's there everywhere, even today it is there. But if our body is immune, we don't get infected. But because of these patients have been immunocompromised, you can see, the bone has been eaten away. So the black fungus, actually, it is so fast, in infecting. The doctors, just the moment they detect, or the patient comes for this clinical intervention, the immediate surgical, the option is that they surgically remove that portion which has been infected, because there is no way they can prevent the infection from spreading. It's like a cancer, like they just cut open. It's like it's a fungus, very fastly it eats into the bone. So they immediately cut that affected part, giving some bone, sufficient safe margin. And many of these patients are left with a lot of difficulty. This is just one, some report earlier. I think in India itself, this is just reported cases. We have more than around 2 lakh people are there. This is just reported. So maybe a lot of unreported, cases, people who have this problem. Um, so the we have started a work along with an company. We are trying to develop these implants, and more than now, 200 implants we have made. So you can see each patient, the geometry, the kind of defect is all different. And for each patient, one has to develop this design specific to that patient. That process itself is very complex, understanding the anatomy and reconstructing that. So like for this patient, this is the kind of the implant that needs to be designed with some specific anchoring locations. And then you have to have these dentures where later reconstruction, one can put some artificial teeth and all can be added at a later point of time. But this is below the jaw line, as you would say, which is like a bone itself is not there. First we have to have foundation. After that we can go for the superficial reconstruction of the gums and the teeth and so forth. So as you can see, each patient's geometry is different. I am just showing you some different types of cases. And currently, even though we have done a lot of this design, we're trying to understand the design philosophy and trying to automate. And a couple of my research scholars are still working on. So close to about 200 patients, we have done this implant development. Uh, Thanks that we have our own titanium 3D printer, metal 3D printer, we get some CSR funding, because many of these patients cannot afford also these kind of metallic implants, 3D printed metallic implants. And we have a network of doctors uh, who through a consortium we are working. And these are some cases that I am just showing. So we have this we call this as a right to face an action that we have come together to look into. And with additive manufacturing we are able to do so currently. As I said, more than 200 successful cases. So in most cases the implants have never failed. The regular infections, any operation, post operations, there are always chances of some, it's not uh, so those kind of cases might have been there, but the implants themselves have not failed in any of these scenarios. uh, so couple of other, some cases, these are some old cases that we have done, in fact this is more than 20 years old. We have done some intervention of club foot correction using 3D printed models and developing the orthosis, trying to understand the force that is required to do the correction and so forth. And so in the interest of time, because I want to give some time for discussion, so some tissue engineering work, particularly in bone tissue engineering, we have developed design methods to represent porous objects, because we can change the pore density and network. In fact, we have a design methodology which is a volumetric representation of the bone density, and which can be translated as tool paths to deposit the material, and thereby we can develop a spatially varying uh, uh, density. So this is in fact patented, again a US patented methodology. And more recently we are working with some biomaterials like PEGDA, trying to look at the printability of that from the perspective of shape memory polymers and applications in dental and other areas. So here what you see is one research scholar's work where he's trying to understand the spatially varying, this is what I was saying, material gradation. We can change the material composition as we print. As you can see here, the percentage of this material pigda is from 2% all the way up to 80%. But there are some issues in manufacturing, like the the geometrical tolerance and form and other things. So we later optimize. As you can see, this is the initial model, and later after optimization, we could achieve a reasonable form tolerance on material. With this, I would like to
We'll do that. Okay.
give some time for discussion. Uh, I think Dr. Kiran can, moderate. Yeah, thank
Yeah.
you.
Yeah. Thank you, sir. Thank you. Thank you for so much of informative session. It was wonderful listening to you as a design for additive manufacturing and the application, particularly to the medical domain and the activities at IIT Madras, phase to right movement and all those. So I take this opportunity to moderate the session for question and answer. So participants, if you have question, kindly unmute and ask the question.
Hi, good evening, sir. This is Professor Omkar from ACS College of Engineering, Bengaluru.
Hi, hi, Dr. Omkar. Yeah.
No, no, sir, yet not doctor.
Okay. I wish that you know you.
Sure, sure, sir. Thank you so much. Thank you, sir.
Yeah.
Sir, we have been talking about metal 3D printers, and
Okay.
now we are already into Industry 4.0. Sir, I wanted to know what are the limitations of the metal 3D printer, like based on the material which can be like which material can metal material can be printed, and also as an aerospace engineer, I am very much curious that why are we not able to build our own engines?
Okay. Um, so, as I said, many of these standardization and qualification, right? Those are very, very stringent. So, uh, today now we have organizations like Semilac, which looks at, say, airworthiness, right?
Yes, sir.
and other aspects, we are trying to have our own standardization. In the medical domain particularly, there are not too many standardization that are there, even now in India. So all the time you have to go and look at, say, some FDA approval, or what kind of ISO standards are available. So in the medical domain, fortunately, so long as the the material mechanical characteristics are retained, and biocompatibility, and the cleanliness, right? The clean room, and other things are established, the implants can be made. But in the aerospace and other domain, the qualification is still very very stringent. That is one reason I would say. But also from the technology wise, unless we are able to showcase the advances in, let us say, capabilities of using some um, novel materials, because the moment you change the material or a process, any of this, that itself requires for, again, all the requalification and everything. So even though lot of work is being done in inconel and other high temperature alloys, I feel that I think this airworthiness and other qualifications, they're quite stringent, and also the reasons could be purely, the commercial, or trying to have some kind of a monopoly on these kind of technologies. That also has something to do with why it's not getting penetrated. But AM is in general trying to, I would say, democratize the ability to manufacture. So it's not that only some XYZ can make say aircraft engines, or for that matter any other component. I do foresee um, that in near future there will be a lot more competing manufacturing logistics which is established. uh, uh, but there's a lot of legacy information, that some of these early people who have been in the business, they have, that data is not available in the choice of making some of these components.
Okay, sir.
Okay. Any
But
other
is it
questions?
only limited to the materials we are exposed to as Indians?
No, no, I think, see, uh, yes, there are many grades of alloys, um, Russian grade alloys, many other grades of alloys are there, whose compositions are not, explicitly known. That is there, that fact is there. But to a greater extent, metallurgically, you can assess the composition, and kind of reverse engineer, right? All the materials, what is the composition, and what is the mechanical property, including dynamic life and all of that. Uh, it is possible. It's not that it's not possible. Yeah.
Yes, sir. Thank you, sir.
Sir, sir, good evening. Uh, Professor Jayesh Dandiya.
Yes,
Sir,
Professor Jayesh. Yeah. Okay.
yeah, Dr. Jayesh Dandiya from
Hello.
Ravi Motors
Hi.
Group Management. Yeah, thank you, sir. Thank you for such a nice explanation and having a variety of problems you have shown. I have got two questions, sir. One is the skull plate which you have shown, and another example of maximal surgery.
Sorry. Sorry. I think I'm not able to hear your
Yeah.
question properly. Uh,
Professor Jayesh, yes, the voice is not clear.
can you tell one at a time? What is the first question?
Yeah, sir, what is the process of the skull that plate is being manufactured by
No.
additive manufacturing? Titanium
Cranioplasty
material.
implant, right? You are talking about the cranioplasty implant. Yeah.
Yeah, 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 sir.
Okay. Uh,
So, which process? Powder metal manufacturing or
yeah, yeah, yeah.
laser?
So this one, okay, I will just quickly go to that slide. So this one that you have seen, yeah. So this one is LPBF. We have used a laser powder bed in titanium, medical grade titanium alloy.
Yes. So,
So
hello,
yeah.
am I audible?
Yes, yes, but yeah, your voice, somehow either because of echo or we are not able to hear clearly. But I hope I tried to answer your question. This is a laser powder bed fusion process, and we have used the medical grade titanium, Ti64, that alloy. Yeah,
Yeah, thank you for the answer. So, one more question. Now, as we know that the all implants, maybe orthopedic implants, they are available. They depend on the anthropometric data based on location and the dimensions and basically where on the globe the people are living. That difference is there. So,
yeah,
how can we see that? What is the scope for researchers to moderate this kind of things? That the implants which are available in the market, they usually come from the Western side. So
yeah.
generally they are in three sizes. So as per our India, even the technology says that it is feasible to have customized joint implants, everything replaceable.
Yeah.
But costing is a matter. And
Yeah.
for the new researchers, what is the scope uh, to take up this problem?
Yeah, so as I told you in see this problem that I had just showed you, this implant design methodology we developed essentially to reduce the cost of designing.
Yes,
And but nevertheless, still this cost and is high because of the mental prototyping. That's why in this particular example, this particular case, this patient needed a patient specific implant. Even the modular implant, the size commercially available implants were not at all fit or fitting for this particular patient. So I think only in those extreme situations where none of the commercial, it is like saying you go to a shoe shop and none of the shoe is fitting to your leg, then only you will go to a person who will measure your foot, and he will make the leather shoe for you, right? So something like that. So here again, this particular patient, the size were whatever commercially available implant, none of the implants were fitting. Even though, as I don't know whether you have noticed, no, some of these research we have done as early as 2000, 2011, 12, 13, all of that. But 2017 and so forth, this happened more in during COVID around 2020, 2021. Also it was because we had our own metal printer and we could print. So this alloy was a cobalt chrome alloy which we used to print for that patient. So the cost reduction again is indigenous technology. So today we have indigenous machine manufacturers. So metal printers costs have come down. So say around 1 to 1.5 crores you can have a starting machine, which was not possible earlier with all the OEMs, and also the powder manufacturing cost. It was not like say some every day, every year as years pass by, our capabilities in this domain is increasing. Earlier, we didn't have so many powder manufacturing companies in India. So today we have several powder manufacturing companies. We are also trying to have on the qualification side, like particularly in this aerospace, Semilac is there. So there is the change is happening, and also the laser technology that is getting people are able to access. So multiple lasers, so productivity, the time to manufacture also can be reduced. Multiple, today people talk about 4 lasers, 10 lasers. So that means it's not one laser which is fusing the metal, but you are having, let's say, 4 lasers, means it is like parallel processing. You can make the component faster, and so I'm told at least China is building like farms of additive manufacturing, like an entire plant having like tens of additive manufacturing machines making components. So I think um, the scenario is changing, and so as I said, technology is uh, maturing, and it is becoming affordable, and a lot of these challenges like developing new design tools to disruptively use am is what a lot of work can be done as researchers, academicians, right? um, Developing design methodologies, developing new, novel materials, because more and more with the indigenous machines, it's not coming to you as a black box. So earlier, even though you might get some OEM machines, you may not be able to change the material. But today, you can play with the material. So that means you can create new alloys. You can create, uh, different applications. I think there's a lot of scope is there for Indian academia, industry, also translating this technology to industrial application, taking it to real world, like where industry adopts. So today with our intervention, there are a couple of companies, at least in and around Chennai, who have put these metal additive manufacturing machines in their shop floor to make this tooling for their industry. So I think a lot of work can be done, both in translating the technology to application, to do academic and scientific research. Every scope, every, I would say, aspect of this technology, we could do research. Yeah.
Thank you,
Yeah.
sir.
Yeah. Yeah, thank you, sir, for so much of a explaining in detail, and also the future scenario and how the technology is going ahead and moving towards its maturity, and soon it will be matured, and technology transfer and all those kind of things. Yeah, any more questions from the participants? Participants, any more questions? Sir, there is one in chat box also I'm referring to, and there Dr. Senthil Kumar posted, is this possible to visit your lab and get some hands-on training for 3D printing?
Actually, we are running some courses for such a requirement, because we are doing it as part of this code NPTEL. There is a platform, right? In NPTEL, I think most of you know, we have this. Um, Course on additive manufacturing. This is the third cohort we are running. It's not just for industry, for any person, where we run the course, and we also offer some hands-on training as part of that. So mm, uh, yeah,
Uh,
it
okay.
is available.
So
uh,
like I'm curious, like NPTEL is mostly the online course, but you
but
mentioned
here
hands-on.
it is a this is also, it involves some visit to the campus in between. So the course runs mostly online as far as the theory
Oh,
part
yes.
is concerned.
Mhm.
Every week, some Saturday, we spend 1 hour online, to clarify doubts and other things. And the
Okay.
other thing is, it goes by the video lectures, recorded lectures, right?
Correct, sir. Yeah, that is a normal mode of NPTEL. Yeah.
But then in between, for this course, because we need practical, exposure, so we also have these participants visit us. So,
Okay.
um, so that is available. Yeah.
Okay. Okay. Great, sir. And this registration you take through the NPTEL portal only.
Uh-huh. There is a code portal. This year, the code, typically in a year we run only once. As we have
Ah, yeah.
too many uh, things to do. So yearly once we do this runs for about 4 5 months, in a slow pace, and like a full semester course only. Some 40 for more than 40 lectures, and like that it goes. Typically it starts in October and
Okay.
goes all the way up to March or something like that. Yeah.
Okay. Okay.
So this is a third set we are doing, and we see
Okay.
lot of industry people, who are coming. So every time we have at least some 10 15, cohort size is there who do
Okay.
this course.
Okay. Great, sir. Great. Okay. So, any more questions? So there are many compliments coming in the chat box, sir.
Oh, okay, I have to
Yeah,
open the chat
like,
box. Huh? Okay, just like
yeah.
I'm seeing my own screen. Just
Uh,
just give me a 1 minute.
uh,
Yeah, let me
mm,
see.
mm. Nice informative session, and thank you and all those.
Where do I see the chat box? Sorry.
It's on the right hand side.
Yeah, yeah, yeah. Yeah, I
Mm,
got it.
mm,
Okay.
mm. Okay, sir. Thank you for the wonderful
There is,
session. It was really wonderful to listen to you and a lot of knowledge. I mean, yes, right from design aspects to the technology and applications. So it
yeah,
was wonderful package to listen to you.
thank
Thank you once again from the Sardar Patel College of Engineering and from the AICT ATAL initiative, AICT, and from all the participants. Thank you, sir.
you. Yeah.
So I close
There
this
is
session.
one question on AIML. So I think a lot of this data analytics is coming in. Like, let's say you have a lot of these defects, and while the component is being built, let's say in metal additive manufacturing, there are porosities. So we have porosities like keyhole porosities, and many such defects are there. So online monitoring and immediate corrective steps, right? To so that before the, because once you make the whole part, and then obviously you detect the defect post operatively. It is like postmortem only, you cannot do anything. If the component has blowholes or some keyhole porosity or cracks, the component is a failed one. So while
Mhm.
the component is being made itself, by sensing, let us say, the laser, the circuits, electrical signals, like voltage drop or many other characteristics. A lot of this informatics, right, can be taken out from the machine, and online monitoring can be done. And lot of AI tools are being developed in that domain. In fact, some work we have also done to understand the porosities, right? What is the cause and how to detect them and all. But yes, a lot of work can be done in that domain also. Yes. Yeah.
Okay, yeah. So that's a new topic.
Yeah.
Yeah. So
People
thank you.
today want to do not
Yeah,
AI.
yeah, yeah, yeah.
People want to do AI in everything. So
Correct. Okay. AI is pulled by every field.
yes, yes, that's true.
Okay, so thank you very much. Thank you. And I close here by this day's session. And for the information to the participant, we'll meet tomorrow at 6, and we'll have first session by Mr. Ronak Timble from the Creative Tools India Private Limited from Pune, and the next session is 7:30 by Mr. Ajinkya Shetty from Siemens. So see you tomorrow. Bye. Take care.
Yeah,
Good
bye,
night.
and best wishes to all the participants. Thank
Thank you, sir. Yeah.
thank you, Dr. Kiran, for this opportunity. Thank you. Bye.
Thank you, sir. Yeah.
Thank you, sir. Thank you,
Thank you,
everyone.
sir.
Thank you.
Thank you, sir.
Yes.